What is our chance for survival if an enemy attacks? One of our primary defensive actions against an air attack will be a salvo of rockets or missiles fired by an Air Force pilot flying hundreds of miles from our territorial shores in a supersonic flight. This will be one phase of an integrated defense system, including guided missiles fired by units of Continental Air Defense and associated commands, supported by United States Navy Fleet Task Forces at sea. If our weapon systems are fully capable of doing the job expected of them, enemy aircraft will be hard put to evade, outspeed, or outmaneuver them. How big is this if? How effective is our defense? Are the men operating our defense systems training under the most accurately simulated tactical situations possible? Radar operators, fighter pilots, guided missile and gunnery crews cannot be trained for split-second counterattacks with slow, sitting duck targets. Realistic training and evaluation of defense systems must be accomplished using targets which will simulate actual enemy aircraft performance and require efficient utilization of time. This time is an all-important combat factor. The Q-2A Firebee target drone missile developed by the Ryan Aeronautical Company for the United States Air Force is tangible evidence of the new trend in supporting systems for training and evaluation. Jet-to-jet, air-to-air, near-sonic combat simulation is a daily game played in deadly earnest by United States Air Force interceptor crews in skies above the waste of the Southwest and over zoned ocean areas. The hunters, Air Force pilots, training against a target that can realistically simulate enemy aggression from the air. Pilots who are sharpening their skills for the kill in answer to any challenge to our national safety. Corey, the elusive, highly maneuverable Ryan Firebee, the jet drone target aircraft of USAF drone squadron. This jet target flies at the high speeds and altitudes of modern combat planes. It is the first target system that provides performance comparable with current first-line operational aircraft. The Q-2A target is a high subsonic, high-altitude drone missile. It is air-launched, remotely controlled, and recoverable from land and sea ranges for reuse. Designed primarily as a target capable of simulating near-sonic enemy aircraft, the versatile Ryan Firebee is used for evaluation of weapon systems and for ground and air crew training. It has potential tactical applications as a vehicle for missile, electronic countermeasure, and reconnaissance assignments with minimum modification of the basic design to accommodate specialized equipment. Special devices for use on the Q-2A to augment certain characteristics are available in kit form for field installation. These include wingtip pods and a tail cone reflector assembly used to augment the radar return when the Firebee is used as a target for missiles which employ tracking radar. A rear-facing lamp pod is one method used to augment the infrared radiation of the jet engine for missiles which home on heat-producing equipment. Advanced auxiliary devices are being developed, including scoring devices and active augmentation systems, which will result in the Q-2A being even more useful in training personnel and evaluating weapon systems. 4 air-transportable Firebee shipping crates with a total weight of only 2,800 pounds are designed to facilitate handling by any common carrier. The Q-2A components can be uncrated and assembled into operational form, ready for initial use by 5 men in only 12 hours. Standardization of parts, simplicity of design, and ready accessibility to all compartments permit assembly line methods of maintenance and interchangeability of components as required. The fuselage, ailerons, elevators, and rudder are of conventional semi-monocoque construction with magnesium skins and aluminum alloy structural members. Empty weight is approximately 1,200 pounds. Gross weight, approximately 1,850 pounds. The 45-degree swept-back wing is a full cantilever construction with heavy-gauge aluminum alloy skin and spars and with magnesium leading and trailing edges. The empennage is of the same type of construction, except that the skins are of magnesium. The 2-section aluminum alloy and plastic tail cone houses the drag and main parachute recovery systems. The compact Firebee has a wingspan of only 11 feet 2 inches, a length of 17 feet 4 inches, and is 5 feet 10 inches high. Fuel capacity is 101 gallons of JP4, oil 1½ gallons. Preparation of the Q-2A airframe for initial use consists first of a visual inspection for possible shipping or handling damage. Then control system check is made for free and unobstructed operation and alignment of the ailerons and elevators and proper installation of control linkages. The pitot-static system and surrounding areas are inspected for cleanliness and the system checked for leaks. The engine and accessory installations are gauged and the engine is moved to the test area. With the engine secured in the run-up stand, the power plant is manually tested and is now ready for a ground run-up. The direct control box is connected by the external power umbilical cord assembly and the engine checkout begins. Following starting procedure and initial engine operation, the maximum engine RPM is checked by beeping the throttle switch until 100% RPM is attained, after which deceleration is effected by beeping the throttle switch in reverse direction. The engine run is completed as fuel, power, and stop switches are closed. The two-stage parachute recovery system, which is stowed in the tail cone, consists of a 6-foot drag chute and a 70-foot main chute. Rate of descent on the main chute is approximately 22 feet per second. A swivel release mechanism separates the main chute from the Firebee upon landing. This helps prevent damage caused by surface winds dragging the target. Qualified military technicians find the Q-2A electronic and autopilot systems not as complicated as those installed in service aircraft. Internally, there are the electrical power plant, stabilization, recovery, command control, and radar beacon systems. Externally, engine starting, pre-launch tests, and launching circuitry expedite pre-flight testing, but add nothing to the in-flight weight of the target. Prior to flight, the completely assembled Firebee, supported in the airframe stand, is moved to the test area for final checks. Then to the waiting B-26 launch plane. Suspended on the bomb rack and the sway braces adjusted, the Firebee circuitry is connected to the launch aircraft through an umbilical connector. Utilizing the external power facility, a complete run-through of operational procedure is accomplished, and the target is ready for flight. The day's operations start yesterday. Before the squadron secures in the evening, 6 Firebees, flight-ready, are on the line. The 3 white-painted B-26s, each carrying 2 gleaming red Q-2As, are fueled, checked out, prepared for early takeoff. Shortly after sunrise, purposeful groups of men are moving to their varied tasks. Command holds a briefing session for the airborne, ground control, and recovery personnel. Line crewmen converge on B-26, H-21, and Q-2A for a last-minute recheck before flight time. Word is passed to the flight line. Pilots and air crewmen man their planes. First telephone calls coordinate power, range safety, ground control, radar, and recovery units. Is a receding dot in the sky, reaching for operational altitude. Radar antennae of ground control begin to pulse in their search for the Firebee on its launch plane, then with steady concentration, lock on as the B-26 approaches the rocket range and begins pre-launch checks at 15,000 feet. Remote command control of the Q-2A provides for climb, dive, turn, trim, level flight at constant altitude, change of throttle setting, smoke signals, and parachute recovery. These commands, initiated by the beeper pilot through a remote control box, are relayed by an MSQ-1 radar transmitter to an AN-APW-11 command control radar set within the Q-2A. A tracking radar with plotting board records information on target position, heading, and altitude. This, in combination with telemetered airspeed, altitude, and engine RPM, is utilized by the remote beeper pilot in maintaining the desired flight path. Ready to launch is signaled, and at the air base, a harsh rattle of commands over a loudspeaker has triggered the organized chaos of a scramble. In a matter of minutes, F-89s and F-102s are scorching the atmosphere. Launch countdown begins. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, launch. And the Firebee drops away from the B-26 in a graceful curve. Loses altitude for a moment, then climbs to 20, 30, 35, 40,000 feet. Accelerates to Mach 0.8, Mach 0.85, Mach 0.9, and begins its elusive game of hide and seek with the searching fighter planes. A turn with a tactical diameter of 15,000 yards under these conditions makes the Q-2A a difficult airplane to chase and an evasive adversary to kill. Q-2A will fly at speeds in excess of 500 knots at 40,000 feet, and upon numerous occasions has been flown successfully at altitudes in excess of 50,000 feet. It has a rate of climb of 10,000 feet, up from 5,000 to 10,000 feet per minute, depending on gross weight. It has been flown to a distance of 152 statute miles from the ground control station and returned to be recovered in a predetermined area. During the next hour, the steady hand of the pilot at the controls of the Firebee at ground control has put the target through its operational paces. Use of inert missile warheads, utilization of parachute recovery, usually permits reuse of the Firebee even after successful firing runs by the interceptors. A near miss recorded in the stock frame by a scoring camera within the Firebee counts as a direct hit on larger conventional jet aircraft. Mission accomplished, the drone is guided to the recovery area and parachute deployment is commanded. The recovery system is initiated on command or occurs automatically with fuel depletion, power failure, or loss of command control carrier. As the Firebee floats slowly toward the desert floor on its recovery chute, control alerts the already airborne helicopter recovery unit, and an H-21 Flying Banana flails its way toward the point of recovery. Originally, helicopter recovery involved major disassembly of the Firebee at the point of recovery, with stowage within the retrieving aircraft. Through use of an external suspension bridle, originated and perfected by Air Force recovery crew members, the operation has been greatly simplified, and the time of normal recovery has been substantially reduced. After the H-21 lands, the recovery crew secures the parachute first to ensure against accidental entanglement with the rotor blades of the helicopter. The autopilot components, guidance equipment, wing tips and pods are removed and stowed. Excess fuel is drained from the tanks. The suspension bridle is affixed and fastened to the helicopter cargo sling, and the liftoff begins. The H-21 hovers to a position directly over the Firebee with all lift cables slack, then slowly rises vertically for a clean liftoff. Flight or separate safety release mechanisms guard against malfunction or breakage in the lift bridles, which might endanger the recovery helicopter. Recovery of the Firebee from fairly rough seas is also accomplished by helicopter or recovery boats. Water recoveries require saltwater decontamination, but impact damage is reduced to a minimum. The water flotation requirement is for 1 hour with 25% of fuel on board. This requirement has been greatly exceeded in practice with one Firebee floating 10 days before retrieval. The individual Firebees have flown as many as 17 flights, with the overall average exceeding 6 flights per Firebee before expenditure. Q-2A is gently deposited on the apron at the air base, lifted to a ground handling cart, and returned to maintenance. Complete reconditioning after recovery involves disassembly of the target into nacelle, engine, wing, empennage, and fuselage components. All compartment doors are removed, and all electronic control, power plant, and airframe units are inspected, repaired, and reassembled. Following reconditioning, the veteran target receives its insignia of service and is ready to return to operation, an integral part of Air Force training for tomorrow.